I want to run AI locally. What computer should I buy?
And that sounds simple enough, but it's not. Because the real answer depends on the model, the size, the quantization, how much VRAM you have, whether you care about speed, whether you need a laptop, a Mac, or a PC. I've tested a ridiculous amount of hardware on this channel for this, and I feel like I'm just getting started.
The opening is correct. Choosing a computer for local AI really does depend on the exact model, its parameter count, the quantization, available accelerator memory, speed, and whether you need a laptop or a desktop. But that is not the answer this video ultimately gives. What follows is mostly a sponsored Replit build, useful as a software demo, risky as a buying guide. We checked the hardware specifications, Replit's documentation, the number on the billing screen, and the prototype's own data. One board has the wrong memory. One desktop is filed as a laptop. One tiny unit error is off by a factor of 8. And the recommendation engine is trying to generalize from just 15 benchmark rows. Here is what is verified, what is not, and what you should actually use to choose a local AI computer. First, the premise gets a green card. Hugging Face's own optimization guide explains why model memory scales with parameter count and numerical precision. In rough terms, full 16-bit weights need about 2 gigabytes per billion parameters. 4-bit quantization cuts that dramatically, but it can trade memory efficiency against accuracy and, in some cases, speed. The video is also right that VRAM alone is not enough. Context length consumes KV cache memory, batch size matters. A model that technically loads can still be painfully slow if layers spill into ordinary system RAM. And a Mac, an NVIDIA desktop, an AMD machine, and a niche accelerator do not share the same software stack. So the first 20 seconds are not hype. They are the strongest part of the buying advice.
Your budget, what kind of computer you want, and it tells you what hardware actually makes sense based on real benchmark data. And I'm building it in Replit. Replit is sponsoring this video, and they asked me to show what I could actually build with it.
The sponsorship is disclosed early, which is exactly what should happen. And most of the Replit feature claims check out. Official documentation confirms plan mode, build mode, browser-based app testing, publishing, custom domains, analytics and monitoring, and an optional feedback widget. Current core pricing also includes monthly credits and parallel agents, although exact allowances and prices can change. So this is not a fake product demo. The agent really can scaffold an application, edit it, test it in a browser, and publish it. The distinction is that software generation and data truth are separate problems. Replit can build the recommendation interface. It cannot make an incomplete benchmark set representative merely because the interface looks polished.
Let's get started. First thing I need to do is actually grab the data from some of my old videos. And I'm using AI to pull the data out. And it looks like this might be harder than I thought. I might actually have to watch every one of these videos. Because in some of these, I'm specifying the model, but maybe not the quantization. Bad. And in here that says, do not invent benchmark numbers or fill missing results. I don't know about you, but from my experience, using AIs, you're never going to trust it fully. It can create an incredible application for you, but the data that you're going to be surfacing and using, that has to be validated. And even though I'm going to put that in there as part of my prompt, we're going to...
To his credit, Alex says the data must be validated. He calls the extraction dirty, admits that quantization is missing in places, and says fake data is acceptable only while scaffolding. That honesty matters. But a public recommendation tool needs stronger guardrails than "we will tune it later." It needs provenance, confidence labels, normalized tests, and a hard separation between fixtures and verified measurements. Then there is the tiny claim that all the data might fit in a 5 kilobit JSON file. As stated, that is false. 5 kilobits is only 625 bytes. 15 benchmark records, hardware names, model IDs, quantizations, speeds, and source links cannot live in that space. If he meant 5 kilobytes, a stripped-down file is plausible. Call this a likely slip, not a scandal, but it is still wrong as spoken.
That much hardware that it would require a database. All that work, and it can probably fit just in one 5 kilobit JSON file, maybe even less. Not actually have that in my data set, but I need to fill that in. So DJX Spark has 128 gigabytes. Save changes so I can update the database right there in line. M4 Pro has 64, 128 here, 32 for the Tenstorrent. AMD 7900 has 32, and I'll have to figure out what that NVIDIA GPU is referring to. The benchmarks table has the link to my YouTube video, which is perfect, and that's the Tenstorrent video that I did. So that GPU is the RTX 5090, 32 gigs, and actually this is the AMD.
Now the important hardware table. Most capacities are right. NVIDIA lists DGX Spark with 128 gigabytes of coherent unified memory. Apple says M4 Pro supports up to 64 gigabytes. AMD lists the Radeon AI Pro R9 700 with 32 gigabytes of dedicated GDDR6. NVIDIA lists the RTX 5090 with 32 gigabytes of GDDR7. Framework sells its Ryzen AI Max Plus 395 desktop with up to 128 gigabytes of LPDDR5X. But those numbers are not interchangeable. Some are dedicated VRAM, some are unified system memory shared with the operating system. Framework says up to 96 gigabytes are graphics addressable. A serious schema needs separate fields for total memory, accelerator usable memory, architecture, bandwidth, and reservation overhead. One generic memory column hides the very differences a buyer needs to understand. There are also two concrete classification errors. First, Framework's Strix Halo machine is the Framework desktop, a 4.5-liter mini ITX system. The prototype labels it as a laptop. Alex may have built a portable rig around it, but a carrying handle does not make the product a laptop. If form factor is a user filter, that misclassification can produce a bad recommendation. Second, Tenstorrent's official Wormhole N300 specification is 24 gigabytes of GDDR6, not 32. It has 2 Wormhole chips, a combined 576 gigabytes per second of memory bandwidth, and Tenstorrent calls for at least 64 gigabytes of host RAM. The apps table enters 32. Then the result card shows memory unavailable. That is exactly the kind of contradiction validation should catch before publication.
I want to show you that because Replit can actually work on 2 things at once in parallel because it can split up into multiple sub-agents, and that's what it's doing right here. I can work on both in parallel. Let me read the current spec schema while prepping the front-end fix. Cool. I had to go through and select the model here. Everything else is optional. I'm just going to try this out. Get recommendations, and yeah, there it is. Tenstorrent Wormhole N300. It's a dev board, recommended. Memory should be listed there, but it's not. But that's okay. We'll fix that. This is an iterative approach. Just like actual...
The app recommends the Wormhole N300 for Llama 3.18b and displays 30 tokens per second at FP8. That may be a real result from Alex's earlier test, but this video does not provide enough methodology to verify it. No runtime version, prompt processing result, decode settings, context, batch size, power, or repeated runs. The honest verdict is unverified here, not false. A single creator-reported benchmark can be useful evidence, but it is not automatically a purchasing recommendation. One transcript correction is clearly verified. Near the end, Alex says the work so far cost $3.41. The on-screen panel reads exactly $3.41, not $341. Replit's development database allowance of 20 gigabytes is also consistent with its documentation.
Do it all is app testing. This is where the agent can be told to go and test the app out itself using an actual browser. Think of it like a stress test. So I'm going to give this prompt right here. Test the entire recommendation flow using realistic and intentionally difficult user scenarios. Check the form, results, comparison view, missing data behavior. We're going to have some of the top. That is beautiful. The admin panel, something I haven't showed you yet. This allows me to actually import real data, and it gets processed and saved to the database. And anybody can just load their own stuff. I'll have to secure it later, okay?
For a real advisor, each result should identify the exact model revision, dense or mixture of experts architecture, quantization format, context length, KV cache type, runtime and backend, operating system, driver version, prompt processing speed, decode speed, batch size, power draw, and total system price. Then it needs enough repeated measurements to compare like with like. Mixture of experts models make this especially important. Only some experts may compute each token, but the full weight set still has to fit somewhere. A useful engine should also distinguish loads, interactive, and fast. Those are not the same verdict. A machine producing 3 tokens per second and another producing 60 can both pass a binary compatibility check, while offering completely different experiences. So what should you actually buy? Start with capacity. For 4-bit text models, treat 8 gigabytes as the minimum for 7 to 8 billion parameter models, with 12 providing better headroom. Plan on 12 to 16 gigabytes for 13 to 14 billion. For 24 to 32 billion, target 20 to 24 gigabytes. A dense 70 billion model typically needs around 40 to 48 gigabytes before generous context and operating system headroom, so 48 to 64 or more is the sensible tier. These are planning ranges, not promises. Long context, multimodal inputs, larger batches, and higher precision all raise the requirement. Opacity decides whether the model fits. Bandwidth and software decide whether you will enjoy using it.
Feedback widget so that you can all submit your feedback here, things you want to see. Now, while it's doing some publishing, you can check out logs. You can manage the virtual infrastructure that's running your application. You can see that all this so far cost me $3.41. Congratulations, your project is live.
For small and medium models, image generation, fine-tuning, and the broadest software compatibility, an NVIDIA desktop remains the safest default. Buy enough VRAM before chasing peak compute. For large text models, quiet operation, and simple single-user inference, Apple Silicon with 64 gigabytes or more is compelling, but CUDA-only tools are off the table. Framework's 128 gigabyte desktop offers unusual capacity for Linux tinkerers. AMD's R9 700 gives real 32 gigabyte VRAM if you are comfortable validating ROCm or Vulkan support. DGX Spark combines 128 gigabyte capacity with NVIDIA's stack, but its 273 gigabyte per second bandwidth means it will not automatically outrun a 5090 on models that fit the 5090. Wormhole N300 is a developer board for people choosing Tenstorrent on purpose, not a generic first recommendation. The final verdict, this is a solid Replit prototype demo with clear caveats. It is not yet a trustworthy answer to its own title. The creator gets the big idea right, the platform claims mostly right, the cost right, and most hardware capacities right. But one wrong board specification, one bad form factor label, an underspecified benchmark, and a 15-row dataset are enough to stop us from handing this app a credit card. As a build demo, B+. As a buying guide, C-. Use the prototype to explore. Use normalized benchmarks and official specifications before you buy.